So I'm Beatriz. I'm a scientist responsible at the Brockhaus sector at the Canadian Light Source, the best suite of beamlines you had the chance to visit yesterday. And I'm going to be talking about in-situ X-ray diffraction. So in-situ X-ray diffraction and in general in-situ experiments is when we do our experiment, whether it's diffraction or absorption or anything else, but also controlling a sample environment, whether it's the temperature or a gas atmosphere or a pressure. Sometimes we apply a voltage if it's a battery. If it's a material that we want to interest in the mechanical properties, maybe we put it in a tensile rig and do push and pull and even twist it during the experiment. If it's a solar cell, maybe we want to shine light on it and measure what comes out of it. Maybe we want to control the humidity. So there are many different environments that we might, depending on the material and the scientific case, that we might want to control. And in this way, we can get the information about the sample while it's doing what we want her to do. And then we get more information that is relevant to get better materials for a particular application. So and this is because, that structure and properties and it's all interrelated in materials. So we have many different environments. Some of them we buy them to control temperature, like a cryostat or cryostream, different furnaces. We got this battery cycler. We have this capillary furnace. So we buy environments following users' interests, what's going to get used more. Sometimes the users have a particular interest and they come here with a problem and they can develop their own environment for the particular case. We help and we support them in the development if they need. Like, for example, there was an industrial user that came to Joel and Adam, and Adam developed this cell here to study in-situ cement sitting and watch the cement while it dries and what crystalline phases are there while it dries, which is important. But cement, look around, so that might be plastic, but the cement is quite important. There's no need to reinforce that. So yes, there's a particular application. There's usually something we can think and the solution and an environment to develop to get more information about that particular system. So in this presentation, I'll present a few cases of in-situ X-ray diffraction and scattering that we have here at the Canadian Light Source, and in general in what can be done here and elsewhere. So one of the most common environments that you can find is just control the temperature of the sample. And when you control the temperature, that will, let's say you increase or lower, you will be able to study phase transitions. Like this is just a demonstration example of potassium nitrate. You know why potassium is the K on the periodic table? Because in Latin it's calcium or something like that. That's why. So this is the phase transition of potassium nitrate, and it goes from orthorhombic to trigonal. And by controlling the temperature, we can easily see the transition, and maybe someone wants to see how reversible it is. And while this is a demonstration, this is more an experimental case that we had back in July, long ago. And this is a high entropy alloy with 5 or more elements. And these high entropy alloys have attracted significant interest recently because they have extraordinary properties. like high yield strength at high temperature. So there's a lot of research in this area. So this one is exhibiting an amorphous to crystalline phase transition. So I'll now present some examples in microelectronics. In Brockhaus, we have quite a unique station that was designed by IBM to study zinc microelectronic films. So this station allows them to do X-ray diffraction while they heat up to 900 degrees C, while they measure the resistivity with a 4-point probe on the sample. They control the atmosphere. They have ultra-high purity helium or nitrogen during the experiment. And they also have optical probes shining on the sample and detectors to detect how's the roughness of this film changing during the thermal annealing. And the whole point of doing this is to study how stable these films are during thermal annealings, which are common during the processing and production of these chips. When you have to grow different layers and do different processes, you have a given thermal budget. So you want to make sure you know your thermal budget and how these materials will endure this thermal cycling. So this is a bit of a schematic view of the IBM station. Some of you might have seen it yesterday in the lower energy Wiggler beam. It's a diffractometer, a linear detector, a robot. It's completely automated, so the experiments can be run remotely while we just load the samples and sit back and watch. But no. So here are the laser probes for the roughness, the photodiodes for, I think we have the temperature sensors on the top here. And it's sitting on a diffractometer. And this is how the sample holder looks like. So we put samples, usually zinc, silicon, or germanium substrates, and then zinc films on top. And this is a video, so hopefully it will work, and you can see how it works, this station. And this is a station open to users with applications that are compatible with this. Is it working? No. Okay, come on. Come on. Okay. There. It's working. It's an old video. It was recorded. It says future Brockhaus, but it's actually the present. So our collaborator with IBM is Christian Lavoie. This station used to be at Brookhaven, at LNLS1, the old one, and then they brought it here. So prior to an experiment, you would load the samples, 4 trays. This is a pneumatic system with a slide. It's going to grab the chamber lid, so it's open the vacuum chamber. The robot's going to come and grab the sample. We usually have all these fields. This was recorded for a demonstration. The robot's going to come here and check with this sensor that he actually grabbed the sample. I'm going to come and put the sample here on the... So there's a heater here. It's responsible for temperature control. And there's also water cooling, so it doesn't melt. There's the locks here. And the slide walks away. So the sample is in the chamber now. Now we proceed to pump and put the selected gas atmosphere, do our thermal annealings, our X-ray diffraction measurements. After this, I'm going to show examples of research that are done in this station. Very compact. It's going to the same process of reverse. Lock here and take the sample out. So we receive shipments of samples that we load, and the experiments can be run by programming long sequences of thermal annealing for many samples for several days. So So if you think you have an application, yes, it is open for users. Oh. So this is one example of research in this station. They were studying atomic layer grown ultra-thin metal nitride barriers for ruthenium interconnect applications. And so they did the thermal cycling of these samples at different rates. And you can see the phase changes when ruthenium starts mixing with the silicon on the underneath and forming ruthenium silicide. And by doing this at different heating rates, they get the activation energy for the barrier failure. Here's another example. This time they have, a nickel silicide films. And again, while heating, you can see how the nickel silicide phases form. They can go back and forth and get reversibility. They can see how the resistance and the roughness are changing at the same time. So the whole setup, it allows them to investigate different growth conditions, to then come up with better nucleation process and come up with films that have better stability and lower roughness. One last example, very quick. This one is a germanium telluride thin film with applications in phase memory change because it undergoes the amorphous to crystalline transition. Right here, amorphous to crystalline, and you can see how the resistance drops right at the onset of the crystalline phase formation. So this is the last and third example I brought about the application of the IBM station. And next, for more in-situ experiments, something that is trending and quite popular now is battery research. There are probably 40 plus batteries in this room, if not more. So it's quite important. And getting to know the anode and cathode materials while they are being cycled and what's happening in the air is important to improve them. So we have an in-situ battery setup. Most frequently in the high-energy Wigler beamline because the high energies are highly penetrating and they can go through real batteries. So this is a real battery here, and the sample position, you can see the zoom, and we have electrodes going to the battery cycler. So we can do X-ray diffraction experiments and see what's going on with the cathode and anode materials during the cycling. So we put that voltage up and down, and you can see the anode material peak changing and the cathode materials changing. So this allows the scientists to see, to investigate their materials and hopefully make them better. Here is another in-situ battery example. This is a battery setup developed by Professor Michael Fleischauer at the University of Alberta. So they have their own, that's another example of a user with particular interest who brings their own setup. We help them with the interface, make sure everything fits in our station. And here's an example of results that he can get with that battery setup. And you can see while the voltage is cycled, you can see all the phases that show on and off the different lithium aluminum phases while the battery cycle proceeds. This particular measurement wasn't made at the Synchrotron, but Brockhaus is quite new. We've been two years maybe in the general users program. And considering that's 2 COVID years, that amounts maybe to 2.2 years. So that's fine. So we're going to soon see results like this coming out of... so this user is coming back in September, I believe. And here's one last example of in-situ battery research. This time, the researchers were studying lithium iron phosphate electrodes, and you can see how they were cycling back on and off, and different lithium iron phosphate and iron phosphate peaks, they go on and off with when the voltage goes up and down. And this is for different HK years here. And in this particular study, they were investigating how this oscillation of the phases happen for different cycling rates. And they found that faster cycling rates led to a more gradual change, almost continuous, of the phases during the voltage cycling as compared to a slower cycling rate, which was more like a 0, 1, either one or the other phase. And they explained that this gradual transition is more convenient for the lifetime of the battery as opposed to a separate phases, either one or the other. And then that comes the importance of the result. That you don't want big phase changes with volume changes or clear boundaries moving in batteries. It's generally associated with degradation of the battery. Now I bring another example. This is a user here, a professor at the University of Saskatchewan, Tim Kelly. So Tim Kelly researches solar cells, and he has been, there, we have a student here. Thank you. So he's a long-time user of the c.l.s. and HEXMA first, and came to Brockhaus when HEXMA beamline program moved to Brockhaus. So investigating solar cells, he's interested in their performance while controlling the illumination, the humidity, the temperature, and well, he wants to see what comes out of it. So he has electrodes connected in his environment too. So he brings this chamber to the beamline, and he's able to see the diffraction peaks of his material while he has, well, light on and off. This is a simulated sunlight where he controls the humidity and the temperature. So he can, for example, study the degradation of different materials in the solar cell and how long they last, how they respond to different water humidity, and things like that. So he's a frequent user, and he developed this environment that's quite useful for his particular research. Now onto mechanical testing. So there's a lot of interest in in-situ testing, and for alloys, steels, well, we wouldn't have bridges probably if we don't know a little bit about steels and alloys. So, and there is a large variety of in-situ mechanical rigs. This is one of the biggest ones. This is a Glive S50 machine at the first Brazilian Synchrotron, and it allows in-situ mechanical testing with let's see, I have no notes here, with, well, applying temperature and force, so you can see with very large samples. Of course, you're going to need a high energy too. And going to the other extreme, so this was a very large machine. You can compare to the size of the Hodge. Going to the other extreme, we have a user in July coming with this. It's about this size. This is a tensile rig for a little sample. So this one is from this commercial vendor here, Razorbill. And he had this user brought his setup, and we did a quick interface to our station, and he was able to measure in situ X-ray diffraction while he applied tension or compression to his samples. And our goal in the future is to be able to put this inside a cryostat, so we'll also be able to control the temperature during this mechanical testing. Here's another tensile rig. This time, this is a 20 kilonewton stress rig from Deben at the diamond synchrotron. And yep, this one is in the beam, it's shared between beamlines I12 and I13. And here at the c.l.s, we have had some tensile, in-situ tensile experiments. Sometimes the users have brought their own stress rigs. We're currently getting a stress rig. We're collaborating with Professor André Filion and McMaster. So he's buying a stress rig that will be shared between BMIT and Brockhaus and whichever other beamline wants it, but they don't have the energies. So that one will be a 5 kilonewton maximum stress rig. And we are also buying another one with maximum of 10 kilonewtons. So depending on the scientific case, you'll use one or the other. And this second one should have also temperature control, so that you can also control the temperature and stress your sample back and forth and maybe see how phases changes, see if the crack forms, follow the crack. And I'm going to show some examples of research that can be done here. For example, this is an in-situ tensile study of austenitic stainless steel during a tensile testing. This is the composition of this particular steel. And here is a couple of peaks, how they evolve during the loading of the sample. And the group observed that this metastable austenite gamma decomposes into the HCP epsilon martensite and the BCC alpha martensite. And here they show X-ray diffractograms before and after the tensile test. Oh, same conclusion here. And here is a bit more detail. They show the stress, and on the right side you can see how the peak area, which is proportional to the presence of that particular phase, changes during the whole experiment, and also the peak full width at half maximum. They can follow the evolution during the tensile, the force application. And with this, they can get phase identification. They integrate the peak intensity. They follow peak positions. So by following peak positions, they can get strain. They can get with the peak width, they can get also microstrain. Combined with microscopy is very nice, because then you can see the deformation twins, but marked here with red arrows. You can see micro cracks. Of course, I think XRD is great, but you always want to combine with something else. Microscopy, absorption, that's always useful. Not as much, but yes, seriously, yes, you want to combine and complement with other techniques. And well, with this study, they are able to conclude that they're able to follow the strain-induced transformation of the gamma austenite in real time. They see the epsilon martensite forming, and then the alpha prime martensite, and they get information about the phase volume fractions, the microstrain, which is relevant for developing better alloys. One last example about in-situ mechanical testing. There is a technique available in some synchrotrons that we want to get here too. It's called 3D XRD. You can see it as grain mapping. So when you do grain mapping, you end up with a three-dimensional view. In this case, it's copper, where you can map every grain shape and orientation, the crystallographic orientation, and you get the lattice parameter, so you also know the strain. And if you do this 3D grain mapping during the mechanical testing, then you can see how any particular grain evolves while you are loading, how it might change, it might reorient, it might grow, or you might see a crack growing. So being able to do 3D grain mapping during mechanical testing has an extra appeal. So I'm done now with the examples of in situ mechanical testing. And I'm going to show one quick example about catalysis. Does everybody here know what a catalyst is? Well, they're super important. They're nearly everywhere. They speed up reactions. Sometimes they make them possible, sometimes they make them much cheaper. So really they are everywhere, and without catalysts, we wouldn't be here. Life would be different. So people studying catalysts, they want to do in situ tests. And for that, well, they want to control the gas going through, they want to control the temperature, maybe they want to see what gases are coming out. Okay. So for that, we have setups. For example, we have this capillary furnace here. We call it the Peter Schupas cell because it was developed at the APS by Peter Schupas. And it's quite handy. So we put the sample in the capillary. There are coils to heat it up, and we can flow gases. And we can measure at the same time. And this is an example of a catalyst study using this capillary cell, where we control the temperature. In this particular case, we flew hydrogen because we are starting from the beginning. We start from the impregnated substrate with the precursor salt, and by flowing hydrogen, we get the reduction of the gold salt, and we see the forming of the gold nanocrystals that are the catalysts. So in this study, they started by characterizing a commercial catalyst and then trashing it and saying, well, ours is clearly better. So in this one, you can see how for the commercial catalyst, when it goes undergoes a temperature ramp, you can see how the rutile. Let's see. So the rutile phase is growing up. The initial phase, the substrate in this catalyst is anatase. So the anatase phase fraction is going down, and with the temperature is transforming to rutile. And while it does that, the gold nanoparticles, they move and they coalesce and they grow. And when they do that, they lose their catalytic activity. Because for gold nanoparticles to be catalytically active, they have to be small. So you don't want them to move and coalesce and grow. And this is what is happening in these commercial catalysts. These ones are useful, for example, in gas and car exhaust systems. So this researcher group, they developed this particular catalyst where they developed this star-shaped rutile substrate where the gold nanoparticles sat on the tip of each of the rutile rods. And then when they subject their catalyst to the same thermal treatment, without and with gold on the tips of this star-shaped rutile substrate template, they find that having gold on the tips of the rutile makes them more stable and better. They have better resistance to that thermal treatment. So the gold in the tip actually stabilizes the structure, and it also keeps the gold nanocrystals from migrating and joining another gold crystals and growing. And here's a comparison of the commercial catalyst with their catalyst. So it's more resistant to temperature. And I'm going to dash over the next slides. And with that, well, they conclude that they have developed thermodynamical stable support materials with an improved morphology, and that the gold nanoparticles on the tips of the rutile rods improve the performance, less mobility and less coalescence. And it performs remarkably with CO oxidation. And let's see, how do you say? How much time? 5 minutes? Oh, 5 minutes for question. Well, then maybe I'll just mention this. Someone's asked about PDF and nanoparticles, and there's something called differential PDF. So, for example, in a catalyst, you have a lot of the substrate material, and you have a little bit, 1% maybe, of the catalytic material. So how can you see that 1%? Well, one approach is to measure just the catalyst substrate, let's say rutile or alumina, and then you measure once you have your catalyst on it, and then you subtract. So it's called differential PDF. And when you subtract, then you isolate the signal coming from your catalyst with gold, palladium, or iron. And then it's quite useful to focus on what you care about. Like here is a gray line is for the titania support, the black line is for the titania with platina, and then the differential one, then you isolate peaks that are related to the platinum catalyst. So this is a in-situ reduction of the platinum precursor, and the platinum peaks start showing up. This is again differential PDF. And well, I'm not going to mention, but there are more applications for in-situ studies. Corrosion, which is very important. Let's see, there are, of course, high pressure applications for people who want to investigate how a material behaves at high pressures. For example, what's going on at the center of the Earth. And let's move on. Well, this is yet another environment. And here are the conclusions. So, thank you. Questions?
Yeah, so any questions on the presentation? All right.
So I just want to ask about perhaps most hated experiment, that is high pressure hydrogenation reaction. Is there any cell designed in broken house which can do in-situ hydrogenation reaction if I want to look the absorption of hydrogen over a palladium surface maybe?
In absorption, so we have had, I'm not sure if I understood the question. Was there are absorption experiments?
High pressure hydrogenation absorption.
High pressure. Okay.
You just need to flow hydrogen gas over as you're taking diffraction.
Yeah.
Yeah, we can do that. It has to be low concentration of hydrogen, like forming gas. Because we don't have a process.
Yeah. So there are two cases. We don't have the hazardous gas exhaust system, so experiments that require a gas flow of a hazardous gas, the requirement is to have the hazardous gas diluted below some critical concentration there. Now, if you want a static atmosphere and a small volume, then you can have pure hydrogen or the X or Y gas, as long as it's a static and small volume. I'm not sure what would be your case. Okay.
Any more questions?
So a regular absorption experiment could be like people come with a microporous materials, let's say a metal organic framework, and you put it in a little capillary. First you heat it and pump it out, so you activate your, let's say, metal organic framework, and then you come up with the gas of interest, and you go letting the, let's say, hydrogen in, and you can see how the structure of that material changes during absorption.
That something which I want to put high pressure hydrogen over palladium surfaces to see how much palladium can absorb hydrogen. what are the like shifting in the question description.
Okay. We can talk about it. Yes.
I have a question about applying for a beam time to do an in-situ experiment, which hasn't been done before. So I want to do an in-situ experiment with a specific setup, let's say mechanical testing, something which hasn't been done before, like biaxial, with a biaxial rig. When I'm applying for the beam time, do I need to have the setup built before applying for it, or?
For a specific new setup, I guess the best approach is to contact the beamline scientist and you start working with him or her, and it will happen together. It's a commissioning and developing effort. Yes.
If there are more questions, maybe she will hang up for a while. You can ask them. So for the sake of time, we have to go to the next section, which is about